Hello, my name is James Hastie. I'm a researcher at the University of Aberdeen in Scotland, and I'm going to present on the structural integrity of composite pipes, specifically under combined thermal and mechanical loading pertaining to deep water applications. This work was undertaken with my colleagues Professor Igor Guz and Professor Maria Kashtalyan. So I'll begin with a quick overview of the video presentation. I'll start with some background. I'll then introduce this thermoplastic composite pipe. I will very succinctly review the current literature, list some aims and objectives, the methodology, present some results, before summarising and mentioning some ongoing work. So, background. Fibre-reinforced plastics are ideal candidates for deep water applications where high specific strengths and moduli, corrosion resistance are obviously very desirable. Historically, composites have been regarded as complex in comparison with traditional steels in terms of their design and analysis, manufacture, and so on. However, as offshore applications extend into deeper waters, there is a need for lightweight materials as enabling technologies, so allowing us to go further than we could before. And interest within the offshore sector has accelerated with the advent of standards and recommended practices, so documentation that promotes confidence. Thermoplastic composite pipe, or TCP, is one such product attracting interest for various offshore piping applications. TCP consists of a structural fibre-reinforced thermoplastic laminate with an inner and outer thermoplastic liner. The laminate itself is made up of multiple plies, fibre-reinforced plies. Various thermoplastics are used, preferred over thermosets for superior fracture toughness, ductility, etc. And the laminate is reinforced with glass or carbon fibres that are laid in a winding process. And TCP is manufactured in continuous lengths and spooled onto drums for storage and transportation, as you can see on the right-hand image. A quick look at the literature. Composite tubes have been well studied under a variety of mechanical loads in isolation and in combination, for example for subsea applications. Literature relating to the thermomechanical analysis of such pipes is somewhat scarce. Typically, studies are limited to analytical modelling consisting of isotropic layers, fibre-reinforced plies, or a sandwich arrangement of the two. These analytical models typically consider thermal load on its own or combined with pressure only. The structural integrity of composite pipes under combined thermal and mechanical loading requires investigation. And doing this by finite element modelling would allow a variety of loads to be investigated once a base model is established. Furthermore, with a finite element model, we could introduce things in future like delamination that might not be feasible to do analytically. And temperature dependent properties should be considered for realistic analysis. Aims and objectives. Investigate the effects of thermal load on structural integrity of TCP operating under loads illustrative of a deep water application. The application we look at is a single leg hybrid riser system, which we can see illustrated in the figure. We recall that risers convey fluids between the surface and the seabed during offshore oil and gas activities. In the system, the vertical pipe is subjected to combined pressures, tension and thermal gradient arising from the mismatch between the temperature of your pipe contents and the external seawater. Analyse through thickness stress-based failure coefficient for different high-low load combinations, so different operating scenarios. And investigate the influence of fibre winding angle. Methodology. A 3D finite element model was developed capable of analysing stresses in TCP under combined pressure, tension and thermal gradient. Here we see an image of the pipe model. The pipe is very loosely based on a real-world configuration without exactly emulating any one brand in particular. Loads are applied simultaneously. Thermal gradient is applied via a fixed internal surface temperature, and the outer surface is exposed to free convection, so to the surrounding ocean. We considered a carbon fibre reinforced PEEK, so very high performance material. Temperature dependent properties of which were compiled and listed in one of our recent papers. And in this study we considered different laminate fibre orientations. Firstly, plies orientated at alternating plus minus 55 degrees from the longitudinal axis, followed by two configurations with 30-degree plies either on the inside or the outside of the laminate. And to evaluate failure of TCP, we do this according to yielding of the isotropic liners, so the von Mises criterion, and failure of the laminate according to the well-known Tsai-Hill criterion. Here we have the stress interactive Tsai-Hill failure coefficient, so-called stress interactive because we account for interaction between stresses in different directions. So, on to some results. Firstly, we look at varying internal temperature on TCP under different pressures. This is for the 55-degree fibre laminate with a fixed tension. Here we see the through thickness temperature distribution for increasing internal temperature, and this corresponds to the three main layers. We see that with increasing internal temperature, there is little effect on the outer surface temperature, with the outer surface being exposed to convection to the ocean. Here we look at the effects of increasing the internal temperature on through thickness failure coefficient, and this is for an equal internal and external pressure of 15 megapascals, so approximately 1500 meters ocean depth. We see that increasing the internal temperature results in a drastic rise in the failure coefficient through the inner liner, with little effect on the laminate and the outer liner. At a higher pressure, at 30 megapascals, we see the laminate is greater utilised, and the effects of increasing the internal temperature on the inner liner are less severe. Let's now look at an internal to external pressure ratio of 2. We see again we have a drastic rise in the internal liner failure coefficient with temperature. And for the same pressure ratio but higher pressures, we see less variation, and again the laminate is greater utilised. So all this tells us is that when we design with high pressures, the variation of pipe operating temperature results in less effect on the safety factor. So that might give us more flexibility when it comes to operations. Let's now look at increasing tension for a pressure ratio of 2. At 30 degrees internal temperature, we see that increasing the axial tension results in an increase in failure coefficient through the three liners. And at 120 degrees, we can see a big increase in the laminate. In the liner, there's some variation with this high temperature. And looking again at increasing tension under higher pressure, at 30 degrees, we see that increasing the tension causes little change in the liners. And at 120 degrees, we do have some variation with the temperature, and in the laminate, we have this big increase. We can see that the laminate is actually expected to fail under this high tension failure coefficient greater than 1. Let's now look at alternative laminate fibre angles. Firstly, for an internal temperature of 30 degrees, pressure ratio 2. Here we have a laminate with plus minus 30 degree plies on the inside. We can see that the failure coefficient doesn't change with tension in these plies, whereas plies orientated at 55 degrees, we can see the failure coefficient increases with tension. And the same is observed, but the other way around for the opposite configuration. We see 55-degree plies on the inside this time still experience an increase in failure coefficient with tension, whereas 30 degrees, again, there is not a significant change with tension. Looking at these alternative laminate fibre angles at 120 degrees, as before, we see that 55-degree plies experience an increase in failure coefficient with tension, regardless of whether they're on the outside or the inside of the laminate. Here we can see some big variation in the liner coefficient as well at the high temperature. And finally, let's look at these alternative fibre laminates under high pressure. At 30 degrees, we see not much change at all in the liners with increasing tension. And as before, the 55-degree plies, we have an increase in failure coefficient with tension regardless of whether they're on the inside or the outside of the laminate. Now here, these dark lines, we see the configuration with 30-degree plies on the inside. Clearly the coefficient is much higher in this configuration than if we have the 30-degree plies on the outside, which is these grey lines. And a similar result is observed at 120 degrees. So, to summarise, results show it is crucial that thermal and mechanical loads are considered in combination when analysing structural integrity of TCP in deep water. The effects of increasing thermal gradient are more pronounced on TCP under low pressures. Similarly, increasing tension has a greater influence under low pressures. So when we're designing for high pressure scenario, varying the pipe operating temperature, the pipe tension has less effect on safety factors. Excuse me. For high tension scenarios, a low failure coefficient can be achieved by orientating outer plies at a low fibre angle. The present model can be used in conjunction with global pipe analysis tools for a global local analysis. And some ongoing work at the University of Aberdeen is investigating TCP under combined bending and thermal load. Various references you can check out if you are interested. And I have nothing more to say other than thank you very much for watching. I would be delighted to address any questions you have at the upcoming online session end of June, and I will see you there. Thank you very much.